Okay, good afternoon, everybody. So we can start the first presentation of this afternoon. It will be about power hardware in the loop, as you can see it on my screen. In the loop, in the electromobility, it will be given by Sante PUGLIESE within the chair of power electronics in Kiel University. Okay, so I think Sante is connected.
Yes.
Okay.
Yes, I'm here. Yeah.
Okay. So good afternoon for you, and thank you for coming to give us a talk and sharing your activities about power electronics within EV applications.
Yeah. Thank you.
You're welcome.
So I will start sharing.
I stopped my.
Okay. Perfect.
Share my screen. Okay, and now you can share your screen.
Sure.
Yeah, good.
Yeah. Okay. So thank you for a nice introduction, and thank you for inviting me to this speech about power and loop testing in electromobility. So I'm Sante PUGLIESE. I'm a postdoc at the chair of power electronics since 2008, and I'm one of the senior staff member. In particular, I'm involved in control of grids, but recently we also had some collaboration with other university like Polytechnic of Bari, in particular with the of a mechanical department, where we opened this collaboration about the use of power in the loop in order to test some active suspension system which can be used to harvest energy from road vibration. Can you hear me good?
We hear you good.
Okay, perfect.
Yeah.
Because I saw unstable connection on my laptop. Okay, perfect. Thank you. So here the outline of my presentation. So I will give you a brief introduction on a real-time digital system at the CIU University. If you will have the chance to come to our department, I will give you an outlook on how is our laboratory looks like, how we use this power and loop test simulation, both for power electronic testing in general, I would say, oriented to connect converters, but also to the electromobility. In this case, I will show you an application, which is this one of electrically actuated suspension system, which was exactly one of this collaboration between our university and the Polytechnic of Bari. And I will give you the conclusion of the presentation. So let's start with the real-time simulation of facilities at the CIU. So we have a nice low voltage microgrid lab test where we have a possibility to connect six converters and microgrids with a lot of penetration of a renewable energy system, which are controlled by power converters. Here on the left-hand side, you can see also that there is a real-time simulator. There's a real-time simulator where can be implemented a model of a grid. If you want to test a specific converter in a more complex grid scenario, and we don't want to build a full microgrid in the laboratory, so we can emulate a generator source in the real-time simulation, and we can interface our converter with this simulation using a power interface, be clear soon, which is called the power amplifier. So which is this rack, which is seen here on the left-hand side of this figure. So by using this power and the loop configuration, we can test the stability of grid-connected converters in more complex grid where we increase the number of penetration of renewable energy sources. So this is one of the aspects, but also in this low voltage laboratory test, we test also this electric suspension system, because at the end, in this real-time simulation, we can model electrical power system, but we can model whatever system which can be expressed in a state space equation with a dynamical model. So we can interconnect different converters in order to emulate, for example, the body of a car with an electrically actuated suspension. So we have also this a new facility, which is a medium voltage laboratory, where we have connection to the medium voltage. We can test in this case. The aim was to test a smart transformer. So which is for of you who doesn't know what is a smart transformer, is a power electronics based medium voltage to low voltage transformer. So one of the capability and one of the reasons why it's becoming popular is the possibility to give DC connection. This connection means that we can connect a meshed grid. We can have access to a DC link where we can connect battery, we can connect directly PV panel just with the DC-DC converter as a front end, so reducing the number of conversion stage and increasing the efficiency of the overall system. So this is one of the features that a classical bulk transformer, which is just a AC to AC transformer, cannot provide. So in this medium voltage laboratory, we can test this medium voltage to low voltage transformer in different configuration. In this case, we use another real-time simulator, which is Opal RT, but nothing changed. So this gives the possibility to emulate a low voltage distribution grid with several loads and test the smart transformer connected, for example, to some battery or some other DC microgrid, and see how they interact together. So we can really test the hardware in a situation where the hardware will experience the same, this will give the same services, and will experience the same power, the same quantities, let's say, even if it's like if it's connected to a real system. Meanwhile, in the reality, it's connected just to a real-time simulation. So this laboratory 6 kiloampere as the maximum circulating power, and we are in the order of megawatt of also auto transformer in order to adjust the different voltage level. Then, since COVID jumped in our life, I was today got positive test, so I'm speaking meanwhile I'm positive. So we are increasing this teaching activity online. So we use this Typhoon for Typhoon Hill for teaching. This gives a good experience to the students in order program a DSP, which will be, for example, the same DSP used to drive an electric drive, but in reality, this will be connected to a real-time simulation where inside there is, for example, the model of a grid or the model of your motor. So you can control it online remotely from home. You can program your DSP with all the control feature. This DSP will interact, giving a PWM signal and measuring from the I/O current voltage, and your controller will behave like it's connected to a real motor. So closing what is called control hardware in the loop simulation, which is different from the power loop, because in the power and the loop, we already mentioned that we need a power interface to connect the converter to an emulated plant. But this one, it will be clear now. So I will show you what the power to test power electronics. So here is given an example of the smart transformer. But this is true for for all new devices which needs to be tested in the field before its commercialization. Okay, so in general, this power in the loop is effective. You can test the converter in a more controlled scenario. It means that if some fault happen to the converter, this fault is not propagated in any point of the grid, but it's limited to the converter itself, because in between there is a power amplifier and real-time simulation. So you can also emulate whatever kind of faults you want to represent, while this one difficult in case of a real grid. So it means that just changing some control parameter or some structure in your emulated grid, you can emulate asymmetrical faults because you want to test low voltage write-through capability of your devices without, let's say, having an impact on a real grid. And one of the capability of this power in the loop scenario is the possibility to be repeated always equal each other. That if I want to test several converter in a production chain, I can test this converter always using the same model of the grid and be sure that is always the same and is behaving exactly as I want for all the tests that I need to do. Despite all these advances, one of the two of the main aspects that we need to take in account when we do this power in the loop simulation is that they should be accurate in order to really reflect what is the behavior of the system that we want to have. And it should be stable. So stability is, of course, the condition that should be always satisfied. What we can say is that the simulation can be less accurate, but of course the stability is a condition that we should be stated always. And typically this stability and accuracy issue are in contrast goals. So it means that when we want to increase the stability of the interconnection, so typically we lose in accuracy, while a more accurate system is more prone to be answered. So, but let's see from really from a scheme what is a power in the loop simulation. So generically, so the device under the test, which is shown here with an hardware, which is connected to a digital real-time simulation, which is shown on the right-hand side, which is represented the model of the grid or a plant, and they are connecting each other, they exchange each other power through a power amplifier. The rule of the power amplifier is to emulate instantaneously the behavior of the grid. So it means that the device under the test at its point of common coupling, okay, it will behave like on the at the other side of the PCC. There is a real grid which is live, which we can change parameters, we can generate spot. He will behave exactly like it's connected to a real grid. The power interface, so translate digital signal in a power variable. So it means that the power amplifier will receive from the real-time simulation something which are signal, could be voltage or current, and the power amplifier will apply this current or voltage at the point of common coupling. So typically we use source power amplifier. So it means that they fix a voltage at the hand. So they typically receive an input voltage as a controlling signal. The way in which we close the loop is called interface algorithm. And we see that this interface algorithm has an important aspect in terms of accuracy and stability. So from this point of view, we can say that if we want to, without losing of generality, let's say that an accurate power and loop simulation it's a system which behave in real time like my naturally coupled system plant. So if this one is the plant that is my ideal plant that I want to represent, an accurate power in the loop is the one that has equivalently, here I put it in terms of an impedance, a same dynamic, okay? The same ZRT should be equal to Z star always. Why I moved to this representation in terms of the impedance? Because typically we use impedance based to study the stability of interconnected system. So this ZRT, which can my plant, as we see here, is represented with an arrow. So it means that it can change during normal operation. So because the grid can be reconfigurated. So this ZRT could be the impedance of the equivalent impedance of the grid seen by the converter at point of common coupling, and I should be able to represent it correctly. And it's a variable impedance because change based on the configuration of the grid, but also it's variable because change based on the interface algorithm that I'm using. So an indication about the accuracy of the system as intuitively is this one. So the best PLL power in the loop is the one which generates an equivalent impedance which behaves like the ideal plant in a wide range of frequency. Here is coming the range of frequency because I'm defining as an error in terms of an impedance. So it means that this an error will be an error as a function of omega. Depending on the particular application, and the particular results that I'm interested in, it could be that I'm interested to have perfect accuracy in a specific range of frequency regardless of, for example, high range of frequency. Could be that, for example, at power system level, I'm interested in be accurate in modeling my plant in a really low frequency range, while I can accept that really dynamic can be negligible from a power system. So in this way, I can represent the accuracy as an error, as the ratio between the impedance of the real-time simulation, equivalent real-time simulation, and the impedance of my naturally coupled system, which is my target. So as I told you, why we need to move to this impedance representation of my plant, because we can use not only the definition of the error with an impedance, but we can also study the stability of the interconnected system. So in this case, my device under the test, could be a grid forming converter, which is connected, is supplying a load. So my grid is just a pure passive load. So actually, I can use impedance-based criteria in this way. So I need to satisfy two conditions. So the first condition is that my converter, so my device under the test, if it's modeled as a Thevenin equivalent, should be stable when it's alone, when it's connected to any load to any plant. So it means that I'm designing the device under the test to be stable. And this depends typically, so it depends on the the controller closed loop. Another condition is that the equivalent plant that I'm representing is the RT, since we will see, taking account some interface algorithm which are intrinsically having some delays, we see that this delay in closing the loop can lead the system to have unstable poles. So one of the conditions that we should satisfy is that the plant that we are representing through the power in the loop it's stable when it's supplied by an ideal voltage source. So when these two conditions are verified, in this plant, the current which is flowing from the device under the test into my grid depends only on this ratio, so which is the ratio between the impedance of the device under the test and the impedance of the emulated load with the power under the loop. So, and this is important because we understand that now the stability, if plant was a coupled system, should be depend only the ratio between the Z device under the test and the Z star. In the reality, this since we are using a power in the loop, we can have some different stability margin, this is different stability assessment due to the fact that we are using an interface algorithm to close the loop. But what is important is that we can use impedance-based criteria, and the stability will depend on this ratio. So we can use just a Nyquist stability criteria, and if this Nyquist is not a circle, the point -1, we are sure that our interconnected system is stable. So see what are interface algorithm just to understand better how can be closed. This is called controlled current type. So we have still the device under the test represented with a Thevenin equivalent. At the point of common coupling, here we are connecting our power amplifier, which is emulated with the voltage source controlled and with a delay. On the other side, on our TDS, we have the model of my plant. As you see here, I'm including also a voltage source. What is this voltage source? This voltage source is a controlled voltage source, which is taking account in the real-time simulation the presence of my device under the test. So at the point of common coupling. So I measure the voltage at point of common coupling. I feed to the into the real-time simulation. I solve this circuit. I solve this equation. I derive the current which should flow in the real-time simulation, and with the controller I compare this current simulated with the hardware current, because at the point of common coupling, if I'm in ideal condition, so the voltage and at the point of common coupling and the voltage in the real-time simulation and equivalently current, they will be exactly the same. So what I do is exactly imposing that the current should be the same, and I give this voltage reference to the power amplifier, closing the loop. Now I will not do all the calculation, but what I get is from at the point of common coupling, I can write an equivalent representation of my interface algorithm and my plant, including all the delay and the controller involved, in terms of an admittance or an impedance. So which was that ZRT, that equivalent modeling of my plant. So in an ideal case, if there were no delay and the control bandwidth of my current controller here could be set as much as possible, infinite, in the reality, what I will have that these terms, sensitivity transfer function, it will go to 0, should be as low as possible. While this transfer function here represent the closed loop, so it means that if I have an infinite bandwidth, the closed loop has a gain equal to 1 for a wide range of frequencies. So at the end, ideally we'll have that the output admittance equivalent will be equal to G star. So at the end, I'm exactly representing my plant. So I'm telling that the device under the test will feed the power into my load or into my plant, exactly like if I'm modeling the real Z star. Due to the delays and due to the fact that I don't have this infinite bandwidth in the current controller, in the reality, I cannot be accurate in a wide range of frequency. But looking to the Bode diagram here, which are representing this impedance, equivalent impedance, we see, so in blue, there is the equivalent impedance of my plant. In red, yellow, and violet, there are the equivalent power in the loop impedance representation. So at the end, I would say that I'm accurate only at 50 Hz. So it means that this kind of interface algorithm, it's good only when I want to be sure that I'm feeding the right power only at the fundamental. So I'm losing information about the low and high frequency dynamic of the plant. Another interface algorithm is partial circuit duplication. So actually, here we use still a voltage source power amplifier. What I'm doing, overlapping part of the hardware. So I'm reproducing part of the hardware. This is inductance, which is used as interconnection between the power amplifier and the point of common coupling, is you see as replicated in this point. So at the end, if I measure the voltage and I replicate it here, and then I measure again the same voltage after the filter, and I ask to my power amplifier to apply it as an output, if there were no delays involved, everything should match. So this voltage and this voltage should be equal, and the current that is flowing should be the same. In the reality, we saw from the impedances that there is an error in the representation of the plant. So Z star is still my RL load. In the reality, with the partial circuit duplication, I'm not accurate, even at 50 Hertz. So this is a promising in terms of stability, but not in terms of accuracy. What we can do is, for example, merge this interface algorithm and use a partial circuit duplication as a feed-forward action for the control at the current type. So at the end, if we represent the equivalent admittance, so you see that is equivalent to the current controller, but these terms, which was the sensitivity transfer function, which has an impact more at low frequencies, is decreased, strongly decreased. So we see that in low frequency, we are much more accurate in representing my plant. This could be useful, for example, if I want to do harmonic stability analysis with harmonic power flow, because I'm interested in low frequency harmonic, or if I want to do studies about subsynchronous oscillation in the grid connected converters. So then from the point of view of stability, I already mentioned you that we can use the impedance-based stability criteria, and we have to fulfill some condition. Here, there are shown some condition about the stability as a function of the gain KP of the current loop. Because what I didn't mention here is that if we increase the KP of the current controller, equivalently increasing the bandwidth of the current loop, but we cannot increase the current bandwidth to the infinite. So as a result, the C will be accurate as see here. So this violet line is perfectly matching with the blue one, but in the reality, we cannot implement no system. The current control loop will be unstable. This instability is shown here because I'm representing so equivalently, I'm representing an unstable plant. As soon as we decrease the KP and we use the right value of this current controller, we see that the poles are moving inside, but we are losing in terms of accuracy. So we have to first fulfill this stability condition, and then we can study the stability of the interconnected system. I already said that we can study using Nyquist criteria, or we can study it using the Bode equivalent representation. So what we have plotted here is plotted the of the device under the test, which is the one in red of a grid forming, which is controlling the voltage at the point of common coupling. And then we have the blue line, which represents our plant, the ideal plant. So if we interconnected these two systems, the overall system is stable. So the naturally coupled system will say that the system is stable with a phase margin of 33 degrees. So this is my reference that ideally, if I have the real plant and real converter connected together. What happens when instead I use a power in the loop to represent my plant? So the impedance, it will change. So it will be this one, which we said has a good accuracy only at low frequency. In high frequency, the effect of the delay will reshape this impedance. So it means that also the phase margin will be reshaped because the point where the two impedances are crossing, it will change. So as we see here, it's crossing now in this point frequency. And at this frequency, we say that the phase margin is not anymore 33 degrees, but is the 18 degrees. So the system is still stable. So it means that I can still connect system. But of course, if there are any variation, so if my system is not well damped, we can increase the damping, putting some shunt resistance. So If it's not well damped, I can occur in a very low phase margin or even negative. So it means that the power in the loop itself, it was going to be then unstable. So this is the facility that we use the kind of analysis. We have a 3-phase 4-quadrant linear power amplifier. Each of these phases is 15 kilovolt ampere. So we have a real-time digital simulation with the minimum time step of 50 microsecond. And here we have one of our 6 Danfoss converter, which are 4 kilowatt Danfoss converter, which was representing my grid forming, and everything is controlled with the D-space controller. How we can validate that exactly we are representing equivalently with the power in the loop an impedance which is different from my real plant. So what we did is an impedance measurement routine. So it means that since we can control frequency and amplitude of the voltage generated by the device under the test, by the grid forming, I have a flexibility to control it, not only the 50 Hertz component, for example, for the grid application, but I can also generate whatever voltage from to 3 kilohertz with a certain amplitude. I can measure the current. I can estimate the impedance. So this impedance, what will be? It will be the impedance of my equivalent load when I use the power and the loop. Here there are shown for each interface algorithm exactly some experimental measurement which prove, for example, how the controlled current type, which is the yellow one, is accurate only at 50 Hertz. For other range of frequency is less accurate. The partial circuit duplication was this red one, and you see from the simulation, from the analysis, and from the experimental results, we saw that this impedance is less. So it means that we will have a current even higher than expected for that load. As soon as we moved from the combination of both, we saw that we have a much more accuracy at low frequency, and especially at 50 Hertz. This can be proved also for hardware and simulation current comparison. So here there is a current at 50 Hertz. You see in a controlled current type, they are perfectly matching. So the current in the current hardware physically that is exchanged by the converter and the power amplifier. When we move to partial circuit duplication, you see the red one is the measured current, is the hardware. It's higher because the impedance, equivalent impedance of the load, is reduced. As soon as we move to a hybrid combination of both of them, so we have again a perfect matching. But what we said that we are interested also to see in a higher frequency. So here we had an example at 350 Hertz where we see that all the first 2 methods are not accurate in representing the model. So the real-time simulation current and the hardware current did not match. So with the controlled current type, even if there is a bit of a phase delay, I would say that it's much more accurate in the representation of the plant. This one was more for understanding what is the power in the loop, what is an interface algorithm, what are the methods to study the accuracy and the stability of a power in the loop. Now we can go a bit more in the application of the electrical actuated suspension. So two are the main tasks that a general suspension should fulfill. One is to provide comfort, so it means that we have to ensure to isolate the smash is the body, the chassis, okay, from the irregularity of the road. The other is from the security point of view is that we have to provide always a continuous contact between the tires and the road face, which is called road holding. So typically a pure passive suspension system, which is made so essentially can be seen as a spring with a damper, designed for some specific kind of road. And when we have fixed the damping and the damper and the spring, those are the coefficients. You cannot change it online. So it means that you have not flexibility. And typically, when you do this design, you have to choose between safety and road holding, because they are typically two objectives which are in contrast each other. So your design should be a compromise. So when we move to an active suspension system, which means that apart from the damper and the spring, we use an electric actuated external force, we can decouple, let's say, these two, we can decouple, sorry, I will answer later. So we can decouple these two designs, so these two objective, and try to obtain a function which is minimizing both of them. In general, we see that here, when we are moving from a passive to a full active suspension system, we are moving this, which is called the Pareto front, lower. So it means that we are much more close to some good behavior of our suspension, both in terms of road holding and so ride safety, and in terms of comfort. So let's see how it can be modeled. So an active suspension system. Here we have only a quarter of a car, so it's a 2 degree of freedom active suspension, where we saw the sprung mass, the unsprung mass, and here there is equivalent spring, damper, and this is the externally actuator, which is between the chassis and M2, which is represented the mass of the tire, while the tire itself is also producing some damping and has some spring, some stiffness. So it means that it can be also a model with the spring and the damper. And then we have the road, which is our input. So the road, we'll see how it can be modeled, but at the end, this 2 degree of freedom system can be equivalently represented with the differential equation, or in a state space model, where the state space are the position Z1, Z2 of the sprung and unsprung mass, their velocity, while the input is ZR, so it means it's the road, is velocity, and FA, which is the force induced by our external actuator. Everything can be modeled as a matrix, in a matrix, and can be used as a model reference to be included in our real-time digital simulator. So this is the reason why with the real-time digital simulator, so this system, even if they were developed for example, RTDS is developed for power system application. In the reality, it gives the possibility to include analysis tool, some state space model. With the state space model, we can represent, of course, I'm neglecting all the nonlinearity of the system, so I'm doing a really simplified model of a quarter of a car, but I can model quite good my car, even using some software which is suitable for power system level. If we want to move to something really for automotive, a possibility is, for example, to use as a real-time simulator. So it has some already pre-configured block and some classes which are more suitable for this purpose. Why, for example, we don't need a specific software? Because, for example, in order to model the road, we can use we can model it using the ISO. This ISO give the expression of the road in terms of what is called power spectral density. I will not go in deep in this one. So the point is that from the power spectral density, we can equivalently in the power spectral density is given as in a spatial frequency domain, not in the time frequency domain. Since we are dealing with a real-time simulation, we have to extract information in the real time of the street, how it's changing the time. So how it can be modeled? So it's equivalent, it can be modeled as a white noise, which is going inside a first order filter. This first order filter, it will change based on the grade of the street, so the roughness of the street. So they will change this parameter. There are grade A, B, C, D, A, and so on. Changing this parameter in this first order filter, we will have all the possible representation of the street for that specific class of street. Everything then should be multiplied by the velocity of the vehicle. So for each velocity, we will have a different road profile. So as you see in this formula, we have a first order equation, whereas in input we have a white noise, and all these parameter depends also on the velocity in terms of meter per second of the vehicle. So when we fix that, we have all the information. We can implement it quickly with this block. You can do also in Simulink. You can do with any possible random noise Gaussian generator. You can, with the block of some integrator, with the first order filter, you can obtain the position of the street and its derivative. So in this way, you model. And as an actuator, we use a tubular permanent magnet actuators. Is a three-phase, so which have a moving part. Permanent magnet are in the moving part, and we have a three-phase windings. So the magnets are arranged with Albach magnetization in order to improve the flux linkage. Here is how will look like an electrical actuator. So at the end, we don't have physically this electrical actuator in our facility. So what we did is representing it equivalently as a permanent magnet synchronous machine. So as like a brushless motor with its equivalent synchronous DQ reference frame model. And from that, we derived the expression of the electromagnetic thrust of this three-phase linear PMSM in this way as a function of the link left fluxage and the current in the Q at the axis. Since in this case, we are using isotropic model, so at the end, this electromagnetic thrust will be only a function of EQ. So which kind of control we use? We control EQ in order to control the force. At the end, we use a field-oriented control in order to control the converter. So from here, it's clear now that the model of the street is implemented in RTDS, the model of the body and the passive component of the car is modeled in RTDS. The model of electrical actuators is also modeled in DQ in RTDS. Of course, what is not modeled in RTDS and is our device under the test is a three-phase converter with this controller, which is, as I said, it's a field-oriented control done in a synchronous reference frame, DQ axis. So where we set ED reference to 0, and we have EQ, which is a reference which comes from the motor in terms of from the control of the motor in terms of electromagnetic thrust which I should provide. What is how is generated this force? The reference for the force and then the reference for the current is generated by using a hybrid Skyhook ground hook control. So this is allowed to obtain the set point. And so the formula is written here. And so there is depends on the velocity of the sprung and sprung mass, and each of them is multiplied by a coefficient, which is chi and chi ground. So chi sky is trying to emulate a damper which is connected to the sprung mass of the car, and of course this is clear that is giving an impact on what? On the comfort, because I'm damping the oscillation of the chassis where I'm sitting. Okay, if I do only a pure C ground control, what I'm doing is including in the model of the controller of the suspension something which is decreasing is always providing a contact with the road. So it means that I'm increasing the road holding. So skyhook ground hook it's just an hybrid control which is taking the benefit of both the controller and can be easily implemented in this way. Now what is needed, derive this coefficient chi sky chi ground. Here there is also another part about the stability, because the mechanical system, when it's not perturbed, it should be stable. So it means that we also to verify which are chi-sky ground that we need to use this chi-sky ground, there will be coefficient which are now added to the passive damper, as you see here, of the tire and passive damper of the suspension itself. Okay, so it means that this is changing the chi-sky ground. They are changing the mechanical system. So I need to define what is the range of variation of chi-sky ground in order to verify that my system, my mechanical system, is still stable. Well, in this case, I have to write the A matrix and do determine the eigenvalue of this new system. So, and all these eigenvalues should have a real part. So lambda 1, 2, 4 should be, the real part should be negative, should not be positive. So here is shown what we did, the analysis, and we saw that only for value of chi-sky and chi-ground, which are both positive, we can satisfy the stability of all the eigenvalues which are involved in my system. So from the point of view of the power, you have to do also some analysis, because we can increase the road holding and the comfort, but another feature of this suspension system is to give the possibility to harvest energy from the road. So we can regenerate the battery where my suspension is connected. So and we did some analysis about the chi-sky and chi-ground to understand with this positive value if we can really regenerate. And here is shown that for any value of chi-sky chi-ground that we choose, we can recover from the street the same amount of power. This is only the ideal that I can take from the road if there were no any losses in my system. That is my maximum power, which is around for the change on the different street on the grade, of course, and change also on the velocity, but fixed the velocity and fixed the street, I have always the same power in changing chi-sky chi-ground. So this gives a lot of flexibility. So it means that I can chi-sky chi-ground in order to minimize, optimize the comfort, and for that I use this minimization. So it's a minimization of the standard deviation of the acceleration of the unsprung of the sprung mass, of the M1. For the road holding, I need to minimize the standard deviation on the difference between Z2, which is the position tire of the road. And from the mechanical power, we say that this mechanical power is also influenced by chi-sky, chi-ground in terms of losses. It is not stated here all the equation, but when we change chi-sky and chi-ground, in the reality, we cannot have the maximum power P in, but we have some efficiency, mechanical efficiency. And in this mechanical efficiency, we need to maximize it. So, and we have this average mechanic power. So how is closed power on the loop simulation? So I already mentioned this one. So we have our device under the test, which is the converter with this control. So it's a downforce converter with a displace controller. which is generating a voltage and so producing a current. This is connected to the power amplifier, and the power amplifier is interfaced to the real-time simulation. The real-time simulation, there is the model of the controller, Skyhook ground hook, the model of the plant, which is the car, the model of my tubular permanent magnet actuator in the Q, and the road profile. Everything is in real time. How I close the loop, I need to calculate the voltage applied by the motor, and the power amplifier, it will apply that voltage at the point of common coupling. It's an interface algorithm that we didn't see before. It's called ideal transformer method. So you measure a current, and this current is going into the plant, and then you measure a voltage from the plant, you apply through the power amplifier. So as you see here, the controller is receiving some signal from the RTDS, which are the EQ reference, which depends on the force of the Skyhook ground hook controller. And in the reality, we need also another information, which is not shown here, which is theta. So the theta is the angle needed for the transformation, because we are working in this synchronous reference frame, and this theta is an information about the elongation of the excursion of the linear excursion of the tubular permanent magnet actuator, which is moving vertically. It's not rotating. Okay. So here there are some simulation results which show how is generate the input ZR and its derivative of a grade C surface with the velocity of 20 meter per second. So here in red are shown the reference reference force requested by the Skyhook ground hook controller, and in black is shown how then the current control loop, the field oriented controller, the current loop of the PMSM is tracking the reference, so generating the right EQ in order to generate the right force. So as we said, then we can also based on the direction of the force, and this is the force, this F, this of the suspension, and the linear velocity of the motor, we can understand even if we are in a generation mode or and so we are regenerating, or we are in motor mode. In this slide is shown a case where we are in a regeneration mode. Of course, from the maximum mechanical power that we can extract from the road, we have to remove the mechanical losses due to the passive part, and we have to remove the electrical losses, which are to the copper losses. So when we remove all of that, so all the other part is something that we can regenerate. So if we need to we request a huge force F in order to guarantee comfort and road holding, there could be a situation where F and V, they are concordant, and in this case we are requesting power from the battery in order to apply that force. But if you choose the right coefficient, which is sky and ground, this force will never be so high to be in motor mode. You tune in order to be always in a generator mode, and meanwhile have a good compromise of comfort and road holding. Here are shown some experimental results. So here are shown EQAD current and some phase and current and phase voltages, which are generated by the requested by the motor and controlled by the converter. In the case of a quarter car with this parameter of sky ground, which are optimized in order to have good road holding, good comfort, but also to be in a regeneration mode. So we see that the mechanical power was for each quarter car then you have to multiply by 4 to have of the full car. So you see that the mean value here, this is the maximum that I can generate, is ideally is this 58 watt. In the reality, because of the passivity, which are still in the suspension, we can regenerate only 48 watt. This is from the mechanical point of view, and we have this efficiency, which is a negative because we are in a regeneration mode. So then we have to remove all the electrical losses, so as I said, mostly copper losses. So in fact, the converter is typically has a really high efficiency. We are talking about 97, 98%. So it's really negligible. So mostly the losses are in the PMSM, in the winding. So as you see here, we have anyway a good efficiency, so 0.93 from the electrical point of view. So at the end, we are regenerating 45 watt over the 58. Of course, the total overall efficiency, the product of the mechanical and electrical efficiency. So this means that if we choose properly, we can even regenerate. As you see, this regenerated power is calculated as a mean value. So it means that we are also perturbating the system from the point of view of the DC link side. So this can be used as a possible feature in order to estimate the impedance, the state of charge of the battery, so to do some ICE test. So concluding, and I think that I went a bit longer than expected. So we saw what is a power in the loop. We saw some interface algorithm, and we saw how we can, the interface algorithm has an impact in the accuracy and stability in different range of frequency. And we saw how can be implemented as a power in the loop, an active suspension system, which has a feature of increased road holding, comfort, but also to harvest energy from vibration induced by the road using skyhook, ground hook controlled suspension. We see that the maximum power that we can harvest depends on the passive component, so which is the stiffness of the tire, but also depends on the speed and the grid of the road. And in general, instead, the maximum, so the really active power that we can regenerate depends also on the electrical machine and on the copper losses, mostly of the electrical machine. However, we can regenerate, and we can, as I said, we can use as a possible input at the DC bus of our battery, battery stack, in order to identify the state of charge of the battery, the state of health of the battery, and doing some impedance spectroscopy test. So, and from here I conclude. So thank you for your attention. So if there are any questions, I'm here. And yeah, there was about the slide. I would say that it's material that there are stuff that we didn't still publish, so this is a bit confidential. So I don't know. I have to. I will let you know. Not sure. I will give to the organization.
Okay. Thank you. Thank you, Sante, for this good presentation. So, of course, I think we have not more time to ask questions. Maybe one or two questions.
Yeah.
Because we have the next presentation at 3 p.m. Okay. So, if you have any question. Rodrigo, you can, you want to ask a question? Or just to share the slides?
I'm just interested in the whole presentation. That's what I asked for.
Okay. So if you have any question, don't hesitate. And maybe just here. Okay. Okay, so if you don't have any questions, so we thank you again, Sante, for this presentation.
You're welcome. If there are any questions, so in the so my email was shown in the first slide. Maybe I will write in the chat. So if there are any further detail that some of you want to know about the chair, about our activity in electromobility, I'm also responsible of a course of grid connected converter and a course of elements of electric drives for e-mobility. So you can directly contact me. So you find the right person at the chair. So I'm always available to answer to any
Very
question.
good. You will be the teacher of this part on the second semester.
This is more a bachelor, but if some we had some, so we have already E-PiCo students. I'm responsible of grid connected converters for renewable energy system. So I'm the lecturer in that course. And I have also in parallel a course of these elements of electric drives for e-mobility, where I showed this system, and of course we are open to seminar on this topic. So actually, there was also a student who was doing a seminar with us on this topic, thesis, and we have this collaboration with the Polytechnic of Bari, and so the system is operative. So that the results are really experimental results. You have a car in your laboratory to test a converter or a battery. Of course, for a mechanical engineer, it would be better to have a shaker where we are really testing the mechanical part. So from the electrical point of view, as our expertise, we want to do design of the converter, study the efficiency, or as I said, we have this converter as a front end from the battery. We can do ICE test. Of course, we are interested in the electrical part, and we emulate the mechanical one.
Okay, very good.
But there is power that we regenerate. So the power amplifier was really regenerating power into the battery of the system, which was connected at the DC link of the converter. So there is a really, what I want to leave here, it's the power in the loop. It means that there is a really power involved, exchanged by the converter and the power amplifier. So the converter was behaving like, okay, there is a motor which is in a suspension, so which is connected to a real machine, a real car. You will not see any differences.
Okay, very good.
Yeah, it's not only pure simulation.
Yeah, it's hardware in the loop, let's say. Yeah.
Okay.
Yeah, very good.
So this is my email anyway.
Yeah. Thank you for all this information. And
you're welcome.
Yeah, and then keep in touch, of course. Yeah.
Sure.
Okay, so now we can go to the second presentation of this afternoon. Will be given by Professor Castillo from CINVESTAV. I think he's connected. Good afternoon, Professor Castillo. Do you hear me? I'm not sure. Marie-Pierre, you are sure that Professor Castillo is connected?
Yes. The camera is getting on. No worries.
I'm trying to. Okay.
Okay.
I'm gonna switch because my camera is not working.
Yeah.
I wanna switch to the computer's camera. Anyway, I will try to, let me see if I can.
So yeah, before starting this presentation, maybe as you know, for the students, Professor Castillo is from CINVESTAV, Mexico, and CINVESTAV Mexico, as I presented to you yesterday. And as you know, is one of the associate academic partner of the master. So as I told you, the role he can propose internship, master thesis, supervise you on your studies, give lectures as it is for today on the winter school, give lesson also, it is possible.
Can you hear me now?
Yes,
sorry,
we hear you.
but it seems that I have some problem with my video.
No problem. Okay, good afternoon again.
Good afternoon.
So thank you for giving us this talk.
Okay.
It is our pleasure to hear you and to have our associate partner, academic partner, participating to this winter school.
Yes, thank you very much for your attention. Thank you very much to you all. And as you have said, Professor Malek, yes, we are participating together with the University of L'Aquila. And thank you very much for inviting us to present my institution. I advise to all the participants that this is not a technical talk, so it's just I'm going to present my institution and some of the programs and some of the projects we are carrying on in these days. So I will start the presentation. I will let me put.
Yeah, you can share your screen. I think you have the right.
Yes. Let me share my screen. I cannot, it seems that I have some problems with, okay, got it. Can you see my screen now? Sorry.
Yes.
Okay. Okay.
Very good.
Okay, thank you very much. My institution is the Center for Research and Advanced Studies, which the acronym is the CINVESTAV. And I'm going to talk briefly about the CINVESTAV and some general problems. And later on, I will introduce the Guadalajara Campus, which is a campus where I'm working on. And let me start that we, CINVESTAV started in 1961 with some buildings. This was a government initiative to have a center for research in Mexico. One of the first center of research that we have that we had in Mexico in those times. And this is the current view of the CINVESTAV with all the new facilities and laboratories and so on and so on. This campus is the main campus in Mexico City, but we will see that we have several campuses in all the country. So what the CINVESTAV wants to do is to perform cutting-edge basic and applied research, training high-level human resources, and provide solutions to what we call national problems, mainly in areas, diverse areas as technological problems or social problems. In particular, this government, the current government, is devoted to trying to solve social problems for the Mexican population. And the vision of the CINVESTAV is to be the leading Mexican institution in research and generation of scientific knowledge. We have several campuses along the country. Mainly in Mexico is divided in states. I don't know, in France, I guess they are regions. And anyway.
Yes, regions, yeah.
Okay, we have states. We have campus in several states, in the north part and the south part, and near to Cancun. This is very interesting for students. We have a campus in Mérida, very near to Cancun, and especially in Guadalajara, in which we have electrical engineering and computer science research activities. We have some numbers from the 2020. We had almost 3,000 students, over 66 graduate programs. At present, we have 610 full-time researchers, 345 graduates in master in science programs, and 249 PhD graduates just in 2020. In Mexico, we have a program, a government program, which classifies all the graduate programs in excellence or not excellence programs. And all the 66 programs in CINVESTAV are recognized in these national programs of excellence by the National Council of Science and Technology, which is the counterpart of the CNR in France. We have had 1,000 and more than 1,700 students from other institutions, and many students which have spent research stays overseas. Oh, sorry. Currently in Mexico, we are the #1 institution in postgraduate and postgraduate programs. Number 4 in Latin America, and the number 109 worldwide, according to the ranking of the Consejo Superior de Investigaciones Científicas of Spain. As of I have mentioned that we have 610 researchers. We have several areas in exact and natural sciences, biological and health sciences, social sciences and humanities, and technology and sciences of engineering. As I have mentioned before, 100 of our programs are certified as excellence programs. Beside of this, among all of these excellence programs, this national council recognizes a special category, which is called international profile for some specific programs which have outstanding results, or for outstanding projects, or for outstanding performance. In particular, among the 66 programs in the excellence profile, we have 33 international competent programs, which is very, very important to us. We are the Mexican institution which has more of this program compared, for example, with the National University of Mexico, which has about 27 of these programs, but considering that this national university has about 7,000 professors, so many times the number that CINVESTAV has. We have had up to now about 13,000 Mexican students graduated in both the master and doctorate and PhD programs, and almost 800 foreign students. So we receive each year a lot of foreign students. At Guadalajara, for example, we receive many Colombian students, but we have received in the last year students from Pakistan, from Iran, and other countries, India. From this graduated, we see that we have 8,000 men and 5,000 women. So we can say that we are an equally opportunity institution for men and women. We are an important ratio of women versus men. This is we are proud of this situation. Okay, we'll skip this. In the international side, we have international agreement with several countries, mainly for academic exchange, both for professors and students. And we try to improve these activities each year. In these 2 years, unfortunately, we could not send or receive many students because of the pandemic. But we hope that this year we will restart with these activities. We have many academic exchange with many scientific and technological research institutions. For example, in last year, we have received about 340 researchers and 321 students, not full-time students, but just exchange students. Up to this year, we have 265 foreign students enrolled in one of the graduate program offered by CINVESTAV. Now, in particular, the Guadalajara campus, you know, Guadalajara is the land of tequila and mariachis. It's a very it's a beautiful city, and this is a photo of our facilities in Guadalajara campus. And we have here the electrical engineering and computer science department. We have 5 areas here, starting by the automatic control group, in which we perform control theory, linear, nonlinear, adaptive neural networks fuzzy logic, robotics, vision processing, drones, and other disciplines. We have power engineering, mainly devoted to generation, distribution, and network stability. The design of power electronics devices like induction DC motors, converters, electromagnetic transients and digital protections, etc. The computer science group, which study distributed computing, virtual reality, etc., etc. We have the electronic design group, which perform research in analog devices, power converters for RFID, digital devices, and the group of telecommunications, on which they study remote sensing, intelligent digital signals processing, digital telephony, etc., etc. We currently we are running some projects in the, for example, in CIoT, which is a program on Internet of Things, a project on industry for projects on aerospace with mainly with the Mexican Army, projects on machine learning and artificial intelligence, embedded systems, telecommunications, automotive software development, and a project which is called Modutron, which we started about 6 years ago. It's a company which is based here in our facilities, and the project consists in the design of a rapid transport system moved by the electrical motors. We have participated in the design of the first cars, and now the company is in the step of selling the first solutions for this these rapid transportation systems. So the electrical departments, some by the numbers, we have produced more than 1,500 conference papers, more than 500 journal papers, more than 100 book chapters. We are 29 professors, and we have graduated more than 780 graduated in the Master of Science program, and more than 270 graduated in the PhD program. Our current population is more than 100 master students and 120 PhD students. As you see, we have more than 10% of women here in these programs, which is a high rate considering that we are in the STEM area. Engineering area, it has not more up to now a lot of attraction for women, but we are improving this situation now. We have had more than 150 projects, both in scientific and technological projects. And we have two programs, the Master of Science program, which is qualified as an international level program, and the PhD program, in which I have mentioned that we have a double degree program with the University of L'Aquila, in which we can send and receive PhD students, and they get both the diploma from CINVESTAV and from University of L'Aquila. We have had up to now about 6 PhD students graduated under this program. we have several research and collaboration with many institutions, academic institutions, and with industry, many projects with local and international industries. And that's all. But I don't know if I will leave some time for questions. And if you have specific questions, I can maybe answer. Thank you very much for your attention. I have been very fast, but
No. If I don't know if there is some questions about the students. So if you can, if you have any question, don't hesitate to ask them.
yes, what I would like to mention that the CINVESTAV is maybe the best place to come to perform a stay, or even to do a full master or PhD program here. So what I want to do now is to I don't know how to do. Okay, right here. Okay, thank you very much. CINVESTAV, it's as I has mentioned before, is maybe the best option if you want to come to Mexico. And Guadalajara is one of the best cities. This is the second largest city in Mexico, but we have many. It's a nice place to spend stay. So please, any questions? Be my guest.
Okay, thank you very much.
Thank you,
Professor Castillo, for this nice introduction to CINVESTAV.
Hi, Jean-Pierre. I have seen
Jean-Pierre is here, is connected. Here. I think also, you know, I think also
many friends.
Hi.
Alain Grumino is connected also.
Yeah. I have many friends. I have spent a year in Toulouse at LAS, at Laboratoire Automatique Analyse Systems. I have spent 1 year, so I have many friends in France also.
Good, very good.
Yes, okay. Very nice to hear you, Bernardino.
Thank you, Jean-Pierre. Any questions from the students?
Yeah.
Hello.
No question.
Can you hear me?
Yeah, we hear you.
Yes.
I had a question. Actually, I have two questions. The first is that this institution, what's the difference, the degree that you give to the students? What's the difference with the degree that we can get from a university? Or is it recognized like a university degree, or because you don't, this institution doesn't have a university title? I want to know the difference.
Yes. We are not a university. We don't have undergraduate students. So we receive undergraduate students for the master and PhD programs only. So in Mexico, we have universities, and our center is a very special case. We have the only center for research in Mexico, let's say as a center of research. But there are many other centers of research, but they are under a university, let's say university frame. But we are a federal institution, so our degrees are recognized by the Mexican, how do you say, education ministry, and our degrees are recognized. So our official degrees. but we are not a university.
I understand. And my second question was that for the students who graduate from PhD level in your institution, is there a possibility to be hired as a full-time researcher after their studies or not? Or like if you can give a number statistically of how percent of your PhD graduates will stay and work as researcher in the institution?
In our institution or other institutions?
Your institution.
Okay, we in our institutions, at CINVESTAV, we have the problem is that I think it's a problem that we have in other institutions as well. The problem is that we have not many free positions. So for graduated, for PhD graduated. But as I can say that 100, and this is 100 of our PhD students or graduated are now enrolled in many universities all around the country. Even the foreign students, we have many Colombian students, even for example, we have had, I don't know if it was from Morocco or Iran. Even this PhD student is now working in a Mexican institution. So 100%. So up to now, all of our, as we are a very, very important institutions, our graduated are very, how can I say, they have a high chances to be enrolled in Mexican institutions. So up to now, all our students are working now, not at CINVESTAV, but in other institutions. I don't know if I have answered your question.
Yes, thank you very much. I got my answer.
Okay, thank you. I don't know if any other questions. So please. Another thing is that this double degree program with the University of L'Aquila, it's a very important collaboration that we have with Professor Stefano Di Gennaro. I was working for many years, more than 30 years. So this double degree program, we have started this program as far as 8 years ago, more or less, and we have graduated about 6 PhD students now. Considering that in Mexico the PhD period is of 4 years. In Italy and I guess in France it's of 3 years, but in Mexico we have 4 years. Also, if students, if any student could be interested, we could also use this double degree program with L'Aquila.
Very good.
More questions?
I have another question.
Yes.
Can you explain about possible scholarships for students, both in master and PhD level?
Okay. Yes. If we receive full-time students, as far as our institution is recognized as an international level, 100% of our students, even foreign students, receive a scholarship. For the master scholarship, I guess now is about in dollars, about $700, $750 more or less, which is a good quantity for Mexico. I mean, it's quite enough to be okay to live and for expenses, living expenses, and for the PhD, it's about a little bit more than $1,000, which is also good. And all the students, foreign and national students, receive the same scholarships. So
Thank you so much.
you're welcome.
Very good. Other questions? We have time for questions.
And we have mariachis and tequila. It's a very important attraction also.
Hello, can you hear me?
Yes.
Okay, hello, Professor. I want to ask you if you have like a partnership with some company related to electromobility. Like for,
Yes. Yes, in fact, we are starting now. For example, I personally have a student, a PhD student working, but he's not as a full-time here in CINVESTAV, but the Continental. We have, for example, we have several students in Intel, Continental, and several other companies. And for example, this student is working with, he is starting his PhD program, but he's working at Continental full-time at Continental, and he will work on electric vehicles, the control using for sliding mode control for hybrid vehicles. For example, this is just an example, but we have several agreement with companies on which students go there and perform their thesis, or as in this case, he's working full-time at Continental, but at the same time, he will work in an argument which is interesting both for them and for us. This is just an example, but yes, the answer is yes. We have a partnership with several companies.
Okay, thank you.
Okay.
Okay. More questions?
Maybe I can share, or Professor Ganes, you can share my email. So if there will be more questions, please be my guest. Be free to contact me, and obviously I can. This was not a technical talk, but we could talk about the, for example, scientific arguments we are working on, or specific argument you could be interested, and of course I have the time to talk about that.
Okay, thank you. Of course, I will share it.
Thank you, and thank you for inviting me. I hope I will have the opportunity to be in France again.
Yeah, of course. We will invite you.
Je peux practice mon français. Je ne parle pas très bien le français, mais je me débrouille. J'essaie de le faire.
C'est bien.
Merci bien.
Yeah, it's our pleasure for us.
Thank you very much.
Okay, thank you very much.
Thank you. Thank you.
Bye. Okay, so I think we have finished the presentation of this afternoon. So we can stop here. and see you again tomorrow on morning.